Okay, so here's a problem. Again, we're drawing the shear force and bending moment diagram for this structure. So let's take a moment to kind of assess the situation. We've got a fixed connection and a roller connection. So if you try to treat the whole structure as a single object, you'll see that it looks like it's indeterminate. But right here at B, there's an internal hinge. So we'll end up with enough unknowns and equations to find reactions at A, internal forces at B, and reactions at C. So I want to do that first, and then use that information to draw the shear force and bending moment diagram. So I'm going to first do the free body diagram for AB. Let's see what we can get from that. So in that case, there's the object. At A, I will assume positive shear force. I still want to keep in mind that I'm trying to find shear force and bending moment, so I'll try to keep those going. And then on this section here, it's going to be an internal force. I think what I'll do is also assume a positive shear force at B. And just to be complete, I'll say there's an axial force at B. That's really my two internal forces. And then I'm going to take this applied load and replace it with a concentrated equivalent. Now it's a triangular load, so we know that the centroid of that is 1/3 the distance from the larger end, which for 6 feet would be at 2 feet, and that the value of that load would be the area under the triangle, or the area of the triangle, which is 1/2 base times height, which looks to be 450 pounds. Does that look right? Okay, so you look at this free body, I've got 3 unknowns, I can write 3 equations, so it shouldn't be too bad. And remember too, I'm not really that interested in the axial force, so I won't pay much attention to that. So let's see, I've got no particular, maybe I'll sum moments at B. I could do it at A also, but I think summing moments at B is a good choice. So I'm making sure that my structure does not rotate about B. So when I do that, the concentrated equivalent force is going to create what kind of moment about B? Positive or negative, using right-hand rule? Positive. So I've got 450 pounds times 4 feet. And then my positive shear at A creates what kind of moment about B? Negative. So I have the shear at A times 6 feet. So it looks like the shear at A is going to be 300 pounds. So I have a positive shear at A equal to 300 pounds. Any questions about that? And then sum the forces in the y direction equal to 0. So I've got my shear force at A up, my positive shear force at B down, and then my 450 pound force is also down. So I should get the shear at B, and that looks to be negative 150 pounds. That means I have negative shear at B of 150 pounds. Is that okay? So really I have enough information. I can draw this part of the shear force and bending moment diagram if I wanted to. Couldn't I? You want to do that or you want to wait? All in favor of waiting, raise their right hand. That is not a majority. This is a democracy. Oh, that's a left hand that cancels the right hand. You went in the wrong direction. I'll just hold on. I'll wait. So let's come down here and do the free body diagram for BC. So in that case, I'll draw that little chunk of the beam. So the values that I chose here are equal and opposite on this side. I will draw the axial force, although we're not interested in it. So there's still the axial force at B. Now, positive shear is up, right? Remember, positive shear is down here. It would be up here. Now, when I actually plug in for that, I'm going to plug in my value for shear at B, and it just happens to be a negative value. That's okay. Now, over here on the right-hand side, where I have my fixed connection, I'm going to have, again, this is positive shear at C, and this is positive bending moment at C, and this is positive axial force at C. I'm keeping all my sign conventions positive. Now the load applied is this triangular load. Again, the concentrated equivalent of that is going to act through the centroid. The centroid is here on the right side, 1/3 the distance. 1/3 would be at a foot. So I have a location of my force at 1 foot, and this would be 2 feet. And what's the value? 1/2 base times height. And that is going to be a, what is that, 225? Is that what you guys got? Yes? So let's do it. So what are we going to do? Remember, I don't know A, but I do know B. So if I come over here in some moments at C, the only thing that creates moment about C is the moment, the load, and my shear at B, which is great. I can find the moment. So let's do that. So again, using right-hand rule for my sign convention, I'm going to sum moments at C and make sure the structure is in equilibrium. So starting over here at C, I do have my positive bending moment with my sign convention makes it positive. The 225-pound force creates what kind of moment about C? Positive or negative? Positive. So 225 pounds with a moment arm of 1 foot. And then the other force would be the shear at B. In this version, it is negative moment. So I'd have minus the shear at B times a moment arm of 3. Now, of course, when I solve for the moment at C, what do I put in for the shear at B? Negative 150. So negative makes positive. So I get what do I get for my shear at C? My moment at C. It looks like I get 150 times 3, that's 450, plus 225, right? What's that? 775? Did I say that wrong?
No, it's 675.
What's 225 plus 450? 675. Yeah. And that comes out to be a negative bending moment, 675. And that's units of pound feet. So last thing I need would be the shear. So I can get that by summing the forces in the y direction. So according to my equation, I have the shear at B acting up. I have the shear at C is down. And my force, 225 pounds, is also down. So what is the shear at C? Well, I move the C to the other side. I've got B minus 250. B is also minus, so it looks like it's 375. And it's negative. So if we did all of our work right, we're going to find out when we come over and draw the shear moment diagram and see if everything matches up. So let's construct a template. So that's an important point, the beginning and the end. Also, we know something important is happening here at B, so I'll add that temporarily. So what do we know that's going to happen at B? What's going to happen in our shear? We're probably going to have a value that's going to equal to the internal shear at B, right? And what's our moment diagram going to be at B? Hopefully it'll be 0. So let's establish the positive X and positive values for our shear, and all of our values will have units of pound. So let's start on the left-hand side. What's the shear at A? It's 300. So I'll come here and I'll say 300. What's the shear at C? I solved for it somewhere. Oh, it's way down here in the bottom. Let me zoom out a little bit. There it is. So it's minus 375, right? So I should land here at minus 375. Let's see what happens. I didn't leave much room, so I'll have to put it down here. So we know that the change in shear between any 2 points is the area under the load diagram. So what's the area under this part of the load diagram? It's a triangle, 1/2 base 6 times height. That's 450, right? And that's negative. So if I start at 300, and I subtract 450, what do I get? Minus 150, right? And look at the shear at B. Matches. That's comforting. What is the slope of the shear diagram? Well, it's equal to the load. So looking at the load, what's the load start here? It's a large number. Is it a negative or a positive value? It's negative, and it approaches 0. So my slope should be 0 here, and should start off at a value positive or negative? Negative. So it's going to start off at a negative slope and go to 0. Huh? I'm sorry? Right? The slope of the shear diagram is the load. So the load starts off at a big negative value and decreases to 0. So big negative slope decreases to 0. Is that okay? Now what? Well, the change in shear over the last 3 feet should be the area under this part of the curve. The area under this part of the curve is 1/2 base 3 times height. That should be negative 225, right? And if you subtract 225 from 150, hey, you get 375. That's great. Now, the slope is going to be equal to what? The value at B, which is 0, and it increases to a large negative value again. So this is going to be another negative value. So we'll get something that looks like that. That makes me very uncomfortable. These are going to be difficult areas to find, aren't they? I will show you this. If you look at this carefully, you do have a little rectangular area, and then what's this little piece here? That's called a spandrel, and if you look in your book, it's 1/3 base times height. That's okay, but over here, we're in big trouble. Because what's happened? We've gone from positive to negative, and there's this guy right here. So that is a point where we know our moment will probably max or min. The trick is going to be finding that thing. That's really tricky. And I'll show you why. Just like we talked before, we know the change in shear is the area under the load curve. Okay, so We know the change, right? What's the change going to be? It's going to start at 300, it's going to drop to 0. So that's a negative 300 change. That's easy. What's the area of the load curve? Well, if you project that back up, it would be this area. And what's that area? Not as easy as it seems. I know the distance is x1, but what's that value right there? Well, it's also going to be a function of x1. And when you find that area, you're going to get a quadratic equation. Yeah, that strikes fear into everyone's heart, doesn't it? And you'll get two solutions for x1. Okay, let's say you can do that, which I know you could, given enough time and resources. Now that I have x1, what do I do now? Well, to find my change in moment, right, is the area under the shear diagram. What's the area of this part of the shear diagram? Off the top of my head, I don't know. This is not a parabolic segment. You'll notice it's not zero slope on either end. I can't use one of our simplified formulas in the book. So now it gets a little tricky. So you would have to write this as an equation, integrate it to get this equation, and integrate it to it. This is where I saved this for last, just because I wanted to show you that sometimes our technique, this is a graphical technique, right? We haven't written any equations. We haven't done any really direct integrations. It breaks down. I could draw the shear diagram, but it's going to be difficult graphically to take that complex shear diagram and accurately draw the moment diagram. I can draw the shape, but I won't be able to get the values because I can't figure out these areas to get my changes. So this is one of these problems that kind of like, I guess, has a negative result, because I wanted to wait to the end to show you that, you know, this technique seems to be the best all, end all, greatest thing in the world. But like everything, it has a limitation. This is where the limitation breaks down. Can you still solve this problem? Oh, sure you can. You just have to start kind of a different track. You would have to write the equation for the loading, integrate it to get the shear, which you can do. It's a polynomial. You can integrate that polynomial to get the moment and plot it. So it's not an undoable problem. But with this simplified graphical technique, we're kind of stuck. So you have to be very careful when you're trying to apply this technique with linear loads. I'll go ahead and just write this in here so it looks like we're going to try. We know the moment here is 0. We know the moment at B is 0. And we know the moment at C. What is it?
Negative 675.
Negative 675. The problem is we don't quite know what's happening in the middle. I do know that since this is a positive area, I'm going to go up. And then since this is a bunch of negative area, I'm going to probably come down through 0 like this. I can kind of discern the general shape. In fact, I'll just kind of do that. No detail. But I'm not going to be able to find that value because I can't find that area very well. So that's where the breaks down. Is this value going to be greater than that value? I don't know right yet. I sense it's not, but I can't tell you for sure. So any questions about this? So you got to be aware of these guys when you see them. So if you were to see one on the exam, for example, your first response probably now would be, don't do that one. Yeah. But not necessarily. Because if this part of the problem wasn't there, then it's much more doable. Because you would end up at a 0 moment, and in this area would end up being probably something more spandrel or... So it is possible. So just don't necessarily run away from them if you see them. I might give you a problem set that both have track the triangular. So you'll have to do one of them. So just take your time and think about it. Be thoughtful. And I guess that's a good advice in all things in life. Be thoughtful.